Hi. So in the first video, we had seen about the introduction of heat transfer. We saw the different modes of heat transfer. We saw conduction, convection, radiation. We saw the laws that were governing it. We talked about Fourier's law. We talked about the Newton's convective law. We also talked about Stephen Boltzmann's law. We saw the different constants that were involved in each of these equations. And now this video is about the second chapter. Specifically, it's about the conduction process. So we will look at how do we derive a temperature profile. Now, a temperature profile basically tells you how is the variation in temperature according to the dimension that you have chosen. Let us say if you are choosing a Cartesian coordinate system, so then we'll be looking at different points in space what is the temperature. So that is a temperature profile. We'll be building a temperature profile, and then we will look at how it initially in the first chapter we said that when there is a variation in temperature, there is a variation in the value of K, the physical constant, the coefficient. So we will be look at how does that affect a temperature profile. We would be looking at what does log mean area indicate, how does it help us. We will also be looking at what does critical radius for insulation mean. So we'll be looking at all these things. So first let us start with derivation of the conduction equation. Okay, let's go with that. So here we have a three-dimensional space. We shall be looking at a small element in the space. Let us talk about this element. Alright, so this is our y-axis. Let us say this is x-axis and this is the z-axis. So this is a small element which we'll be observing. So we find that it's a cube or cuboid, whichever you want to consider. So here we shall look at, let us say this element, on this element the heat transfer process is occurring. So let us say in this direction, which is the z direction, that there is a qz heat traveling. Let us say from the other side, this face, there is a qx in the x direction, and then let us say from the bottom side there is this qy. So there is a heat that is going from the bottom of the q, right? Now as the heat is entering, the heat may or may not go out, but let us say there's a part of the heat that leaves the system. This is the system that we are talking about. This is the control volume. So here we have qy plus dy. I'll just explain that what this is. This cube y plus dy, and in this direction you have qx plus dx, and in this direction it's into the paper, so from here you have qz plus dz. Here I just told you that this is an element, but I didn't tell you what are the dimensions of the element. So these are the dimensions of the element. In the x direction it is of length dx, in the y direction it is length dy, and in the z direction, which is inside, is length dz. So this is our cuboid, and so here we look at how heat is entering the system through these three variables and how heat is leaving the system through these three variables. Now since there's an energy interaction going on, the fundamental principle we will be using is conservation of energy, right? So conservation of energy. So this is what we'll be using. So how are we going to conserve energy in this field? So we will say the energy net input in the system, which is your dx, dy and dz system, this cuboid, this net input of the energy, let us say this is our first term, plus any heat generated by the system. Heat can be generated by the system. So this is what is getting inside the system, right? Net heat input and the heat generated. So this is our second term. This should be balanced by the increase in internal energy, because if you're giving heat energy to the system, it will, that energy will be converted to, in some ways it will be converted to the increase in internal energy. Energy plus some work can be done by system, right? Work done. So these are our third and the fourth term into consideration. Now let's quickly look at this term. This term says work done by this element. We are taking a static element, so work done is 0. That is because we know that for work being done, displacement should happen, and we are saying that the element is static, so there is no displacement, meaning this term is naturally equal to 0. Now we need to find out what is net heat input, what is the heat generated, what is increase in internal energy. We'll go by the simplest one first. Let us go by heat generated by the system. So we will say this Q dot is heat per unit volume, heat generated per unit volume, right? So if we want to know what exactly this second term is, my second term will be essentially be equal to Q dot multiplied by volume of this material. Because it is heat per unit volume, you multiply volume to it, you get the heat energy from it. So what is the volume of this material? It is a cuboid, so it is dx into dy into dz, all the three dimensions, length, breadth into height. So you get your volume. Now coming to increase in internal energy, right? This is our third term, as you mentioned. The third term, it is nothing but your mcp dt by dt. How this is representing your internal increase in internal energy. So this is the rate of change of temperature with respect to time. Cp is your constant coefficient with respect to pressure, right? And this is your mass. Now the mass of the system is nothing but density into volume, and volume, as we told, is dx into dy into dz. So this essentially third term becomes rho into dx dy dz into Cp dou T by rho T, right? Now coming to a more important term, more important expression, that is the net input into the system. Remember, we are talking about the net input. So there is an input Qx in the x direction. There is also an output Qx plus dx that is going out of the system. So the net input is the difference of these two. So this is what is entering into the system. Similarly, this is in the x direction. We have in the y direction, we have the similar expression. Also in the z direction, we'll have a similar expression, right? Now what we know already from the previous chapter, what exactly Qx, Qy and Qz will represent. We know that Qx is nothing but minus Kx, K in the x direction, into area of that of this surface. You remember, this is the area normal to the direction of x, right? This is normal to the direction of x, and temperature change in the direction of x. So it will be dt by dx. So first is we'll expand what this ax is. So this is minus kx. This should be normal to the surface of x. Coming back to the diagram, we see that this direction is x. So if you look at this surface, this is representing your surface which is normal to x. So if you look at its dimension is this breadth multiplied by this length. This is the area. So this is nothing but qz, and this is dz, and this is your dy. So this area becomes nothing but dy into dz into dt by dx. Similarly, for qy, you can corollary write it in a similar fashion. You can write this as dx into dz into dt by dy, and qz can also be directly written as minus this should be ky, this should be kz, and this is dx into dy. Because if you look at it, this is our z, it's into the paper, so this is the area that is normal to it. So look at this length, this is in the direction of x, and this length is dx, and this vertical is the direction, is in the direction of y, so this is dy, so the area is dx into dy. So dy into dz. Now we have got our qx, qy and qz, but we need to know how is qx related to qx plus dx. Now your qx plus dx can be written as qx plus dou qx by dou x into dx. And why is this true? This comes from Taylor expansion. A very easy way of understanding this would be that this is nothing but the slope, the gradient of how qx is changing in the direction of x, and you multiply it by dx. So just to give a very quick example, so if let us say this is my x direction, and this is here, this is q, how it is changing. So if I know my slope, and I want to find that if this is my entry point and this is my exit point, I want to know what is my exit point. So then I would take the slope and multiply it by this distance dx, so that I get my this end point. So this is essentially that expression. Now we know that our net heat input was given by qx minus, sorry, q of x plus dx. So if you look at this term, there is already qx here and there is a negative sign here. So you can see it cancels off the qx part, right? So essentially you will end up getting minus of dou qx by dou x into dx. Now how can this be written? It can be, you can simply bring this out and you can expand this qx which we had written earlier, which we had written here, this one, right? So this is what we'll write it here. So we'll write this as minus kx into dy dz into dou t by dou x, and remember there's a dx here, so there's a dx, right? So we can take this inside, but for the moment let us just keep it. Similarly, we can obtain an expression for qy and qz. I can elaborate it if you wish to, but for the constraint of time, let us just know that it is corollary to this expression. Right, so I'll directly write what is the term that we get, this the first term rather. So we have, let us cancel this minus sign out. So we'll have dou by dou x of kx dy dz dou t by dou x into dx. Then you will have dou by dou y, this will be a plus sign, dou by dou y of ky. You will have dx into dz dou t by dou y into dy, plus you will have dou by dou z kz. You will have here dy dx and dou t by dou z into dz. Now to quickly explain it, you see that this is taking partial differentiation with respect to x. Since the three coordinates are independent of each other, you can remove dy and dz since they are not a function of x. You can just bring them outside. So essentially what will happen is this term outside will become dx into dy into dz, right? Similarly, the same argument holds here. X and z are independent of y, so you can bring them outside. Y and x are independent of z, you'll bring them outside. So all the three expressions on the outside will have dx into dy into dz, which is nothing but volume of the object. So you can just to quickly illustrate, you can write this as dou by dou x into kx dou t by dou x. It will become nothing but dx into dy into dz. Similarly, dou by dou y, you will have ky dou t by dou y into you will have again dx dy dz. Similarly, dou by dou z into kz, you will have dou t by dou z, and similar volume. So at the end, our expression, if we bring all the terms, term 1, 2, 3 together, which we have obtained, the one we obtained just now, we know this is 0. Heat generated we had obtained here, right? And increase in internal energy was obtained here. So we will bring them all together, and so we can write this as dou by dou x kx dou t by dou x. Let us kind of make it much simpler. If I just put let me just cut this part out. Let me just write it as summation in the terms of dimensions, and we will put this as a kd dou t by dou d plus you have q prime into volume dx dy dz. Remember, there's a volume term here, and you will have this is equal to your rho into cp. Let me just make sure I write it correctly. Yeah, so you have dx dy dz into dou t by dou d. You see, this volume term is common, this is volume term, here there is again a volume term, so all these three gets cancelled. So what you obtain at the end after such a long process is dou by dou y ky dou t by dou y plus dou by dou z kz dou t by dou z plus q dot equal to rho cp dou t by dou t. So this is our differential equation, which is giving us the temperature profile. So this is the final output of this process. So we can do one thing. If we assume a steady state process, then the term dou t by dou, this thing becomes 0, because steady state means no change in time, no change with time, so this becomes 0. If we say no internal energy, then we say that q dot is 0. So in similar ways, we can get a Poisson form of equation, we can get a Laplace form of equation by giving such conditions. So this is just to briefly explain this part, right? Now let us so now we have actually derived what does conduction really, the equation for conduction look like. So when we have an element like this, we will end up with an equation like this describing the temperature profile. Now if we try to simplify this equation and say that there's only one dimension involved, so we can simply just write this as dou by dou x and no heat generation as well as a steady state. So we can write this as k into dou t by dou x is equal to 0. So this is our one-dimensional equation for a simple plane wall, kx, if we want to say that k is varying with x or not. So this is that this is the equation for a single dimensional heat transfer. Now how can this be used? Just a quick example, how can this be used? So if we have a wall, let us say temperature is T1 here, this is our x direction, x is 0 here, x is equal to some length L here, and this is temperature T2. So we can find the profile of how the temperature varies. Rather, let me put T2 a little below, just to show that T1 is higher than T2. So we will find that the temperature actually decreases from T1 to T2 inside the wall. It keeps decreasing as you go in the direction of x. So how can we get the expression for this? We will integrate this equation, apply the boundary conditions using this this situation, and we'll get an expression for that. So just to quickly illustrate how that is obtained is dou by dou x into, let us say, k into dou t by dou x is equal to 0. So let us first integrate this once. So if you integrate this once, you get t dx equal to c1, right? Now if you integrate this again, integration, you will get k equal to t into c1x plus c2. This was an integration constant, again you integrate it, so you get another integration constant. Apply the boundary condition that at x equal to 0, t equal to t1, which you can see from here. At x equal to 0, t is t1. At x equal to L, t is t2. So we will apply the same boundary condition, right? So if I apply it here, we will say k into t1, x is 0, so c2. So this is the value of c2 we have got. Then we apply the second boundary condition, k into t2 equal to C1 into L plus C2, but C2 is K into T1, right? So we will get the value of C1 from here. So C1 can be written as K into T2 minus T1 by L. So now we have both the values of C2 and C1. So we can write T equal to C1 is K times this term, but we are going to divide this by K, so this will get cancelled. T2 minus T1 by L into X plus the term C2, which is T1. So this you can see is a temperature profile. So you put any value of X here between 0 and L, you will get a value of T at that point. So if you put X equal to L by 2, you will get that at midpoint of the wall what is the temperature. So this is called a temperature profile. Now we have seen a temperature profile. Now let's go and have a look at what does quickly 2-3 simple concepts. One is what is the meaning of log mean area. This is essentially used when you want to convert one form of a surface to another form and see how it is equivalent in some sense. So for example, if you have a cylindrical pipe, let us say, so this is your inner radius Ri, your outer radius R0. If I cut this pipe and stretch it open, it essentially becomes a block. It becomes this rectangular kind of block. So if you twist it and then turn it, it becomes a pipe. If you cut it open and spread it, it becomes a block. So this block, this length is same as nothing but R0 minus Ri, because I've just cut this is this thickness, this is the same thickness here, right? And there are same temperature differences between the outer surface and let us say the inner surface, right? So I have not shown you how the equation is derived for the cylindrical surface, but essentially what the idea is here is that Q, since both the surfaces are same, because I've just cut it open and spread it this way, Q would remain the same. It'll pass the same way in the of the same amount in this surface as well as in this form. So Q equal to you have 2 pi KL T outer minus T inner by ln of or let us say T inner minus T outer by ln of T outer by Ri. I've not shown how this is arrived at, but we can see this later. Similarly, for this block, which is same as a wall, we can use the formula Q equal to K minus K what do you call you have minus Ka dt by dx essentially. So if we want to derive this derive a value of Q in terms of the length of the pipe as well, so for that we would actually be using the equation we just derived. We had derived this temperature profile for a wall. Now what we do know is this value, right? Now we do know what is dt by dx because we have t as a function of x. So if I do dt by dx, I'll actually get dt by dx is nothing but t2 minus t1 by L. So I'll substitute this back here. I'll get this minus Ka t2 minus t1 by L, right? So essentially now I have got what exactly is Q for a wall, given a one-dimensional wall, to be more specific. So since I have told what is to find out the log mean area, we will say that this the Q in both the cases should be the same, because they are essentially the same material, they're essentially the same object, they're not different. So if we equate these two expressions, and let us say this is a mean, all right, because this is, we do not know what is the surface area, right? We are not sure of this surface area, so we'll say let this be a mean. So now if we want to derive it, we can say that 2 pi KL Ti minus T naught by ln of R naught by Ri is equal to minus KAM. Now this minus can be removed and said as T1 minus T2 by L, right? So T1 minus T2 and Ti minus T naught get cancelled, the K gets cancelled, and we want the value of you have 2 pi kl L square, right? So essentially equating these two parts would give you the value of a mean, right? You can get the value of a mean from this part. So this is about logarithmic mean. We have studied so much. The final concept that I would like to discuss quickly in this one would be the idea of what is a critical radius of insulation, right? Because there are frequently questions asked on this part. So to quickly understand the theory part of it, the theory part says that when you have a wall and you add insulation material to it, right? If you're adding insulation material to it, it essentially does not change the surface area. I mean, the area is still the same. The face area does not change in case of wall. But if you have a pipe and you're putting an additional insulation around it, let us say more insulation around it, you find that the outer radius keeps increasing, right? So the surface area also keeps changing. So when you're adding insulation to a pipe, the surface area changes, but when you're doing it to the wall, it does not. So this change in surface area actually affects the resistance of the body. How does it affect the resistance of the body? We understand that for a fluid medium, we saw that Q equal to H into A, T infinity minus Ts in the first chapter. So this system, remember that a heat system can be equivalent of an electrical system wherein the current is same as the heat is the same as the heat, and the difference in temperature is same as the difference in voltage, the potential difference, right? And the remaining part, whatever we find in the expression, is nothing but the resistance. So if I say what do you call Q equal to T infinity minus Ts whole divided 1 by H into A, this is nothing but my resistance, because my current I is equal to V by R, right? So V is my potential, is same as temperature difference, I is same as heat, R will be same as this term. So my R is given by 1 by H of A. For a cylinder, we saw that it will be Q is all equal to 2 pi KL T infinity minus T or T inner by outer by ln of radius outer by radius inner. So I can get the resistance for this case as ln of R naught by Ri whole divided by 2 pi KL, right? Now we see that as we are adding insulation, R naught is increasing. We find R naught keeps increasing. So if you look at this expression, as R naught keeps increasing, this resistance will actually increase, because logarithmic function, as you keep increasing the input value, the logarithm function increases, right? But if you look at the resistance, convective resistance A naught, it is 1 by A naught. It is proportional to 1 by A naught. So my A naught is increasing, which is actually equal to 2 pi R naught into L, my outer surface area. So my R naught is increasing, my A naught will increase, but my 1 by A naught will start decreasing. That means my convective resistance will start decreasing, right? So it so happens that as you keep increasing your R, your convective resistance start decreasing. And we know if resistance decreases, the flow of heat will increase, right? But there is also this simple logic that if you keep increasing insulation till infinity, there should be no heat transfer occurring, because at so much of insulation, no heat can actually pass through. That means there must be some point, that is, when you're increasing the insulation, your radius is increasing, there must be some point that Q starts actually increasing because of decrease in resistance, goes to a certain point, and then starts decreasing again, right? So this point wherein you can have maximum heat transfer in that system is called the critical radius, and this can be easily obtained by following normal differentiation. That is, if you have Q as a function of the radius, outer radius rather, then you can simply do df by dr naught equal to 0 and get your r critical radius from there. I'm not showing the derivation because of the time that is being consumed, but this can be quite easily shown. So in this chapter we had actually seen a few 2-3 concepts. One was deriving the basic conduction equation from an elemental mass. We saw that that equation can be used to generate a temperature profile for the body. Then we saw what does log mean area mean. How does it help us in understanding that a cylindrical object can be considered as a wall and similar equations can be applied. We also saw what exactly is critical radius of insulation, the theory behind it, and the derivation was not done, but it is quite straightforward in terms of how it is to be proceeded. And so basically this covers our conduction equation, though the few things to be reminded of: I have not derived the equation for a cylindrical coordinate system or the spherical coordinate system, which I think I would do in the third video, just to separate it out. And this is it. This part basically covers the theoretical part of conduction. Thank you.